All right. And so, like I was saying, today we're going to talk about today's study group is supposed to be like on A/B testing. Um, but I'm kind of leaving this a little bit open because A/B testing, in my opinion, is pretty straightforward. Like most of it's going to be the lab part and kind of performing it forward. So it's useful for us to kind of go over parts of like statistical power and like how that relates with each other on what's it called? Like effect size, alpha, and all those parts. I also know there's a mention about ANOVA too, so we can also go over ANOVA as well. So we can definitely do that. And if you guys have any questions, just feel free to kind of jump in. Okay. Let's hear it. So this is my repo here that I use like for basically all my like notebooks and stuff like that I'm going to kind of share with you guys. So I'll just put this on the Zoom chat right now. But this hopefully kind of makes it a little bit easier for to navigate through like what sections are and what notebooks. So if you want to go back to a notebook and kind of like play around with it or whatnot or review it, you can check that out. It's an open repo and everything like that. So that's what I'll use today. Cool. All right. So let's see here. I guess I would start off with if there are any, because I know there were a couple questions that people kind of DM'd me. Are there any general questions about statistical power that you guys would like to go over? And I know that was like from last time, right? Go for it, Ricky.
I'll be that guy. But as I look at it more and more, I'm like, yo, this doesn't make sense. So I kind of get where effect size is calculated from. It uses Cohen's d, and that's pretty much to get a sense of how closely related the information is.
Mm-hmm.
Let's see. The other part was alpha size. That's something we usually don't determine. We usually set it as 0.05. But I'm still missing, I think I'm still missing something. And yeah. It's more so with regards to the graph, like what the overlay means, how we calculate it.
Mm-hmm. Yeah, so let me, go ahead.
Yeah, I didn't know if we need to do it by hand, because I've been trying to approach it like that. If I could do it by hand, then I can code it.
Right, yeah, so statistical power can be kind of a tough one because, let's see here, I kind of go through this. This is what I would normally go with my students if we were talking about statistical power and stuff like that. But essentially, it's kind of weird. I think the reason why we call it, I mean, really when we're talking about statistical power, we're really talking about how many false negatives we have. So type 2 errors, right? And so that's usually represented with beta. So note that like type 1 error is alpha, the first letter of the Greek alphabet, and then beta is type 2, which is like, the second letter of the Greek alphabet. That's the way I kind of remember it. We usually don't quote it as beta. We usually talk about it as power, right? I'm gonna close my window. It's getting a little bright here. Darkness, good. All right. But beta is kind of, the reason why we call it power, first of all, is because it's like saying, oh, it's a positive number. So as we increase power, that's what we want. Basically, we want to have less and less, false negatives, right? That false negative rate. So one thing to note is that to calculate this relationship, this power, it's basic, how do I say this? It'll depend on the test. So if you're doing a Welchs Ttest versus a student's T-test versus another test, your power will be different calculated because basically it's dependent on what the shape is. And so I think I sent on the chat a little bit about this little visualization, which I just love, absolutely. Is basically understanding statistical power and significance. They have a few different visualizations, but I think this is a perfect one. So I'm actually gonna go into this n here. So we're gonna calculate n. But the point here is that we have essentially, I think these are, I don't know if he actually talks about it, but you can imagine, oh, this is based on a one sample z-test. So these are like z-tests, but you can imagine a t-test or whatever test you're looking at. So we have our null hypothesis and our alternative hypothesis, right? And so we have these two different distributions. And you can imagine basically, depending on what the effect is. So let's say the effect is like this big. Let's go reset the zoom. There we go. And so essentially we set our alpha to 0.05, right? And that basically says how much are we allowed for our type 1 errors? How many false positives are we allowing, right? And this part right here is basically how many false negatives we're getting, right? So you can see this is our type 2 error. So this is gonna be like, our power is gonna be 1 minus this guy. So what we're really doing when we're saying what is the power, we're really saying how much crossover can we expect using this effect size, this significance, and this, for example, sample size, and with this alpha as well. So you can imagine if we increase, for example, our alpha, we're accepting more power, or sorry, not more power, we're accepting more type 1 errors, then that's going to decrease our power right here, or what's it called? It's going to, let's see if I can make this, well, I guess we're keeping our power. There we go, this makes more sense. As we increase our significance level, we're going to increase our power. Essentially, we're saying how many things are we not going to how many false negatives are we allowing to accept. So you can see this blue, this dark blue here getting smaller and smaller because most of it, I'm gonna do one tail, there we go. As we get a higher and higher portion of saying, oh, we're gonna allow this type 1 error, we're allowed more false positives, we're gonna basically decrease our type 1 error. And that's gonna increase our power. So we can see, hey, we can increase our power, like awesome. We can just basically set our alpha level to like, you know, I don't know, 0.67, and like, cool, our power is 100%, awesome. What's the problem with this if we set our alpha too high?
We'll have more type 1 errors.
Good. So that means in our tests, we're more likely to perform, we're more likely to get type 1 errors. And when we say type 1 error, what's another way we can call type 1 error? It's either a false positive or a false negative.
Positive.
False positive, right? So false positive is saying we reject a null hypothesis when in fact we really shouldn't have, right? So that's the way, like, for example, if our p-value is 0.1 or 0.15, with an alpha of 0.67, you're like, cool, statistically significant. But you know, it's like, wait, we usually have our alpha as 0.05, and so our p-value has to be lower than 0.05 in order for us to say it's statistically significant. That's for us to avoid that false positive, saying the alternative is true, right? Or we say it's all likely to be true. We reject the null hypothesis. So that's kind of like what this power is representing, is like this trade-off between essentially this alpha, this sample size, and this effect size. So we can imagine if I increase the effect size, so that basically means if I increase the effect size, what's going to happen to these distributions? Are they going to get closer or further apart?
They're going to be close. It's going to be a more narrow distribution.
Right. If I increase the effect size?
Yes.
Okay. So let's see real quick if I increase this to like, it was like 0.38, it looks like. If I increase it to like 0.7. So you can see here, it actually kind of spreads out, right? And that's because there's a bigger effect. When I say effect size, right, we're really saying how far are these going through. And I think that's maybe what you're describing, that they get more narrow in the sense that like these guys kind of become more narrow. Is that right, Matthew?
Well, it's not that the actual means of those two hypotheses change. It's just how the shape of the curve and how much.
Right. Right, that's right. Yeah, because there's two ways you could do it, right? One is that the mean actually is different, or one is that it's more, the standard deviation is smaller. So there's kind of two ways you can think of effect size, and they can combine both of those parts, right? Because if the means are very different from each other, then you need a larger standard deviation to get a small effect. Make sense? Cool. All right, so yeah, so as we get a higher effect size, we can basically have less crossover, which means even with this more, let's say, reasonable significant level of 0.05, we're less likely to have false negatives because the difference is so big between the two. The effect size is so different from each other, from the null hypothesis and the alternative, right? Think of this as our control group in our treatment group, right? So our group 1 and our group 2. That means that we're less likely to have that false negative going through. If we have a very, very small effect size, that could either mean that the mean's relatively close, or just the standard deviation, right, is much smaller, right? Or sorry, much bigger, we're gonna have a lot more crossover. So you can see here is that there's a lot of crossover where we'll accidentally basically say, oh, null hypothesis, so the alternative, you can see there's an actual difference between the null and the alternative. This false negative right here is saying when we perform the hypothesis test, we say, hey, oh, we fail to reject the null hypothesis, which basically says there's no difference between the null and the alternative. So our power is relatively low, meaning that we're more likely to actually get a false negative result. Does that make sense?
Yeah. Yes, Clara. So quick question.
Yeah.
You said the size or how our distribution is shaped is depending on the type of test we use.
Mm-hmm.
So for this one, it says that it's using a z-test. So everything is standardized and is centered centered like on 0. So what would it look like if we were to use a different test like the Welchs T or a standard t-test?
Yeah. So the Welchs Ttest then would basically, so when we say a z-test, if I had like a nice, like if I were to make like a nice little chart, let's see if I can do this real quickly, kind of to emphasize my point, is that like if we had like, let's say this is like z-tests, this is a Welchs Ttest, And then these are the different values, kind of like what we talk about. So we talked about like, you know, the z-score, right? Then we have something like the t value, right? And then we had something like distribution shape. So it's like the shape of the distribution. We know this would be a t distribution, right? And that depends on the degrees of freedom and stuff like that. We have heavy tails and things like that. This would be a normal distribution. So what this would look like, let's say if this instead was a t-test, it would actually look exactly the same in that sense of like, you know, the mean and value, because we can always adjust the mean, right? We can always like subtract the whole thing over. Really what's going to change is actually the shape of this distribution. So let's say we have some kind of t-value. It would look something like, let's say, like this, like for this graph. And then let me go ahead and use a different color, like, ooh, I don't know, green. Is anyone colorblind by chance? No, good. All right, that makes my life easier, but just to make it easier. So we'd have another similar t-test or t-distribution like this, assuming that they're the same size. So like this. So you can see this would be more like a student's t-test where they have the same distribution. And you can see our crossover is going to be slightly different because of the shape of the graph itself, or sorry, the shape of the distribution. If we had instead like a Welch's t-test, well, Welch's t-test, what's the difference between Welch's and students?
Oh, with Welch's, well, Welch's is usually used when you don't have all of the underlying assumptions of the regular students.
Mm-hmm.
That's all I got.
Okay, no, it's true, right? And that's good. So for anyone, right? What is the assumptions? What is one of the assumptions that why we would use a Welch's over a student's?
If you don't have the mean?
Not quite. So it turns out it's equal variances, and that's the big part of when we use a Welch's over a student's t-test. So a Welch's test, I won't change over to different, I won't switch over to different notebooks, but a Welch's t-test basically takes into the fact of how many samples each distribution, whether you're, what's it called, your control and your treatment group, if they have the same number of samples and if they have the same variance. So if they have different variance, which is going to be your standard deviation, that distribution really should be wider. But a student's t-test assumes that there's the same, what's it called? Essentially the same shape, essentially the same number of samples and the same variance. So Welch's t-test says, okay, like if you have a different variance and a different samples, you really should be using Welch's, which means it's a different shape of your t distribution. So essentially what that would look like in a Welch's like t-test is you would have something like this is your first graph right here of the, let's say the control group, right? And then let's say the alternative group has more samples for some reason, or the higher variance, or let's say a lower variance. So let's say the variance is very, very small, right? Well, that means basically this graph isn't going to look identical like this alternative hypothesis. It's going to look closer to like something like, I'm trying to draw it really quickly without getting too, well, we'll just go like this. It's going to be like a higher, a lower variance where maybe, this isn't super accurate, but you get the idea, is that we have something that looks like this, where it's going to have a much smaller variance. And this allows us then to compare these two. So the power of a Welch's t-test is going to be different calculated than compared to a student's t-test or a z-test or other basically distribution looks. So the idea, the reason why we say the power really depends on what kind of test you have is based on the fact that there's different distributions that we're using to see what that crossover is. Does that make sense to people? Cool. And one thing I will note is that Welch's t-test pretty much is like always like use a Welch's t-test. Back in the day when you didn't have computers, it might be more effort to do a Welch's t-test. You're like, oh, student's t-test is probably good enough. Welch's t-test, what happens if the variances are, what if the variances are equal to each other and you use Welch's t-test? What happens then? Did bad things happen?
It's going to look like the student t-test.
Yeah, good. I saw a head shake from Matthew, and right, Rakeem, is that it's going to be the same exact thing, right? Basically, it simplifies to the student's t-test. So the important aspect to remember is that essentially Welch's t-test, you're like, might as well just use it because it does, there's no harm done even if the variances are equal to each other. Okay, cool. Does that kind of answer? Rakeem, I think you were the one who first asked kind of like a little bit difference. Did that kind of explain a little bit the difference, like how this power or how this graph would look like different if it was a different test?
Yeah, so pretty much, at least in the example, what it's just showing is which ones are type 1, which ones are type 2, and how they're affected by significance level, effect size, and sample size.
That's right. Yeah. And you can imagine the sample size here. Another last kind of quick question. What if I increase the sample size? First of all, what will the graphs do? Or sorry, the distributions do?
Yeah. I think it's like what Andrew said earlier. I mean, not Andrew, Matthew. It'll get narrower or more peaky. Something like
No, the standard deviation will go down, or the variance will go down.
Yeah, variance will go down, which basically looks like a skinnier distribution. Perfect job, right? So yeah, you can see here, if I really increase it, you can see here, you can see it's kind of going off the table here. It basically gets a skinnier and skinnier distribution, which means we have a smaller beta, which means a higher power. So essentially more data gives us a higher power, right? And a lower data, or small amount of data, has more of that distribution kind of spread out when we have a lower power. Cool. So that's kind of like how you would essentially calculate power. Essentially, it takes in the fact that our alpha level, our sample size, and our effect size will determine our power. Okay. Does that make sense to everyone? Cool. And they're all interplaying. And note that, like, how do you calculate this out? It's easy to just essentially, hey, let's use a package to do that. Because why bother with all that stuff? And I think, for example, use sklearn or stats models. There's some equivalent to figuring out what the power is from that point. Okay. So any other questions on power in general?
I guess for me, sorry, I mean, did anyone else have questions? I feel like I keep bringing up something else.
No, go for it.
I guess for me, it's like, okay, now that I think I see the connection now between the different tests we were using or we were learning and power. And now for me, it's like, okay, after you do all these different tests, whether it's Welch's, students, Z-score, Z-statistic, and now you get to this whole thing with power. How do you then from there, in like one of the examples, do you accurately pick the information you need to calculate your power? Then from there, go into your A/B testing.
Right. So yeah, this will be fun with our A/B testing. This leads perfectly into what A/B testing looks like, right? So what we've kind of been doing, probably like going with Raphael, but definitely the curriculum, it kind of is like, all right, we have these different groups, hypothesis tests. Here's your alternative, and here is your control, your different groups, right? And say, okay, what's the power? Basically, you have this distribution already made, and you say, okay, what's the power? What's the Cohen's d? The sample size is already predetermined. Basically, we already know who's in these different distributions, right? We are usually just define, like the biggest thing we probably define in our hypothesis test is really significance level. So really, all this stuff is pretty determined already, if that makes sense. So like, really what comes down to the fact that it's like, oh, we already have the distribution. We already know, well, we already have the data basically already put in place. We really have to decide on the alpha. And once we put in alpha, we can say, okay, basically plug and chug, as like my math teacher used to say. You plug and chug it and basically say, all right, this is going to give us basically what's our p-value, and this is say, okay, from that distribution, what our power was, since we already know the sample size, the effect size, and all those parts, which will be different from our A/B testing. So what we've done so far, probably in the curriculum, I keep saying like we've done, but obviously you guys done it with Raphael, is you already have the data all put in place, and you just say, all right, is it significant or not? With A/B testing, it's kind of a little more meta in the sense that, like, okay, before we do any testing, we haven't gotten the data yet. We basically say, hey, we have two different groups, our control group and our alternative group. We want to test this out, but we want to make sure it's only worth our while to do this if we can show that there's a certain effect size. So the biggest thing that we don't have determined, right? We can say, like, before we do our test, we can say, okay, we want to test on an alpha significance level. We want to test on a certain effect size. We want to basically say if the effect is big enough for us to make a change. So the classic example for an A/B test is changing like the layout of a website and seeing the number of visitors who either click on it or enroll into like the website and stuff like that. So okay, what if we make the button blue? What if we make the button red, right? Maybe the button right now is red, but what if we change it to blue? What is that going to do? That's kind of like our treatment group, our kind of experiment group. And say, okay, we want to change the button to red, and then collect the data and then say, okay, is there a difference between the two? The big part of that, that we can, the thing that we want to control for, or we can control for, is how many people do we bring into the test. So the straightforward part is like, oh, let's just test everyone, right? So if we test everyone on the website, we're just all of a sudden just flip a switch and see if we change the color to blue to see if they enroll more. What's the problem with that from a practical standpoint? If we just change the color to blue, it's relatively easy probably. Let's just assume it's easy to change the color to blue. But what might be the issue of changing everyone's button to blue? So what if the blue button, oh, sorry, go ahead, Rakeem. Mm-hmm.
Oh, no, Matthew was about to say something.
Oh, I was going to say it. You may not, while you're dealing with the actual production website, you don't want to mess up what's going on right now with your test.
Right. Yeah, exactly. What if you change the blue button and it makes everyone not enroll at all? You're like, oh shoot, like I'm just losing all these customers now, right? And you're like, oh, like sure we have data and now we know, oh, that's a bad idea. But it would have been nice to like test it on a smaller group before we actually make that change. So the thing is like we want to say, well, we want a small group, but how small do we need it? And that's where basically our A/B testing comes down. It's like, hey, what's the N that we have? So we basically instead say, okay, we're going to look at a significance of 0.05. We want an effect size that's worth our while. So say it costs money for us to like, make this change and stuff like that. If the effect size is different enough, then it's like, okay, it might be worth us actually spending the money to get more people enrolled. And then we actually set our power, which usually is just essentially, see if that's the right direction. Usually we set it to like 0.8, basically how many false negatives are we allowing ourselves. So these are usually kind of more or less what we already have decided, right? Kind of standard. And the effect size is really the big part. It's like, hey, depending on like what you're doing and how much this costs monetarily, that's kind of like the thing that we'll set. It's like, okay, we want an effect size of this value. In this case, we're using Cohen's D. It's like, okay, in that case, we need 30 people. And this is essentially what you're doing with A/B testing. You're determining how many people do we put in to this test and say, okay, we need to get 30 people for each sample, essentially, for our control and our alternative. And then we're going to perform the experiment, flip the switch for alternative, our experiment group, change the button to blue, see what happens, give it some time, and then say, okay, and then do a hypothesis test and say, was it significant or not? Okay. Does that make sense? Yeah, so that's kind of more or less like what A/B testing is. Basically, the biggest difference is that first you decide how many people are going to pull into your test, right? And then once you do that, say, okay, I want these different values to set these in stone. And you say, okay, that means I'm going to get so many people. Let's say, for example, 30 people. You pull 30 people basically into your test, and then you do your hypothesis tests. So essentially, like I like to say, A/B testing really is hypothesis tests, just with one extra step where really you're deciding, from these values, how many people you should pull in.
Okay. And quick question, just to make sure I'm on the same page. But you said with the power testing, once you have your power and your significance level set, and you adjust the effect size to see how many people should be enrolled within the A/B testing.
Mm-hmm.
That's how the power also plays into A/B testing to see, I need this sample size to see if it's that significant when trying one versus the other.
That's right.
Okay. So is that code along? We can also do too, just to see what that process and workflow would look like as we're writing scripts.
Yeah, we can do that for sure. Let me go ahead then. I'll go into a little bit of notebook of like A/B testing because there's some parts of like, because like this is in my sense, like this is the easiest part. It's like, oh, you usually use a function just to calculate this part, basically determining these significance, this power, and this effect size. And then you'll get an M, and then you perform the test. But the big part is saying, how do you perform this test and what do you do? Which is really the big part of A/B testing is experiment design, making sure like your experiment's gonna be worth it. So I'll go through that part and then we can do a little bit of code along, kind of like show like what that looks like. Sound good? Cool. All right, so let me go ahead and pull up A/B testings. Cool, so let's minimize this guy. Okay, so I'll kind of like go through this part. I won't read the whole thing through, but like I said before, basically those different parts, your type 1 error, your type 2 error, your effect size, taking those into consideration, you basically put those into an equation, or sorry, a formula, and say this is what the sample size should be. Okay, so we kind of showed about what this looks like. So one thing to kind of note is that like when you should use A/B testing and when you should be really carefully when you tread lightly. So essentially the real reason why you would use A/B testing is if you want to introduce a new feature, right, to old users. So you should say, is this new feature, is this new format, is this new thing that I'm going to do going to affect some target, some metric, right? So there's a few things to consider though, because you're introducing a new feature to old users. So there's a few things called couple of things to consider: novelty effect and change aversion, which kind of get thumbs up if you guys have ever heard either of those terms before. Okay, I see the thumbs up. Maybe just kind of, it's probably pretty self-explanatory, but we'll kind of talk a little bit like what this is. So these are considerations you should do when you do an A/B test to kind of consider what kind of like, whenever you do an experiment, you should always consider like, how could this go wrong? So the novelty effect is basically the fact that like when there's the new thing that comes out, there's always a group of users who are just like, oh, cool, this new, really awesome thing. So the thing is, it's kind of like if there was a change in this thing, maybe there's also, by introducing that change, also you have a huge different change, but that change won't last over a long period of time. So I don't know about you guys, but like whenever like I have like an Android phone, and like I'll like, download the newest Android, update, and I'm like, oh, cool, and I'll mess around with it and everything like that. Same thing with like, like if there's a new like update, like TensorFlow just came to 2.0, there's an alpha in place, and I'll kind of play around with it. You're going to have like a different effect, basically, because people who are really excited about using it will kind of like be excited about using it. So you have to be careful about like what that change is first, right? But over time, this eventually will kind of sort itself out where it's no longer new and stuff like that. Okay. The opposite of this is change aversion. So I kind of like think of it like old man syndrome. It's like, they always like basically grumpy about any kind of change. And so like you always have to be aware, like, some users like, it's like, oh, I hate this new, the new operating system. Like how many times have you heard about this probably like with new updates of technology? Like, oh, the new iPhone or the new, Android phone, like, oh, it's completely trash. Like they got rid of this thing, like I love this thing. And then like a year later, no one cares at all or never talks about it. Or maybe they do keep talking about it, right? So this is the thing, is that you want to kind of avoid these parts where either it's new and exciting or people are like stuck in their ways. So how do you avoid this? Kind of simple answer is just basically you just give it more time. Like essentially you get two parts. Basically you wait, I like to say like you wait for, users to die and be replaced by new users. So for example, if you make a sudden change, most of your people are going to be like, essentially users have already been there, but over time, as you gain more new users, you eventually, they'll be replaced by these, like people who have already been well established in there. So that's something kind of keep in consideration. And I say die, meaning like, oh, there's just more people who are using the service, or, new people who haven't been exposed to the old way of doing things. Other thing too, is just you could just wait for basically users just to get used to it. And this, again, just gives more time. So those are things to consider before you actually do an A/B test. In the sense, like, just know that the first results coming out might not be representative of what you will see in the long run. So, and what exactly are those timings? It kind of depends exactly what you're looking at. So this all depends on like domain and stuff like that. Does that make sense to everyone? Any questions on like that's just like novelty effect, change aversion? All right.
So, sorry, quick question. Mm-hmm. So both of those are mostly like just preference, like how a user or population's preference will affect whether a certain change is utilized a lot or not utilized at all.
Right. So it's kind of like if you ask a bunch of users, like, do you like the way the website looks? People who are already using it probably will say, yeah, I like the website, right? And you realize reason, oh, I don't need to change the website because everyone's super used to it and everything, or people like it and everything like that. The problem is that that's only talking about people who've already used the product, right? So you're kind of like biasing it towards people who already are gaining towards it. But maybe if you change it, there are more people who will actually come in and be, who weren't part of that group of already users. So that's kind of like what I'm talking about in this kind of scenario where you're like, oh, you're really trying to test out new users. And that's what, with A/B testing, it kind of comes down to the fact that you have to make sure you get a populate or a sample that's going to be representative of the users or whatever you're testing that will be in the future. That makes sense? Okay.
Hey, Victor, could you also say that that novelty and change aversion are basically measuring the fact that you just have a change rather than measuring the change itself?
That's right. Yeah. And that's where like classically, like so many businesses will like make a change and like, oh wow, like people are really upset about this, you know, we need to change this immediately. Where in reality, it's like, well, that just might be because there's an initial just change. Everyone hates change essentially. So, well, not everyone hates change, but people are affected by change in different ways, whether that's a good thing or a bad thing, but that's not what the overall effect you want. You know, I'm sure you can think of like all these different examples you can think of in your head, probably like when there's a new change of how people reacted. So always something to keep in consideration. So kind of going off of a little bit of like what I was saying with like the change aversion and what was it called? Novelty effect, is that really what you want to do is you want your samples to be representative of the population they're going to do. So basically, what is your population going to look like in the long term? So like if you're getting more users, if you only have 1,000 users and you're expecting to expand, you want to make sure that you're not just testing off of those 1,000 users who are already enrolled in your stuff. You're like, you want to test on people who have not been, so the larger population as you kind of grow. So I don't know, the best thing to do is the random selection. So really what the change aversion and novelty effect really represent is saying you have to make sure that they're representative of that population. And so note that also random selection is really important. So there's a few things you can kind of think about like where people classically do it. One is, for example, in surveys. Surveys are notoriously awful to like get any kind of feel for like what the kind of data goes through or like what the data represents. So like, does anyone, let's see here. I can think of a good quick scenario, but like if you imagine like if you just gave a survey to people who are already using your product, they're already going to have a certain bias towards how they use that product or what they want in that product versus to people who have never been exposed, which are the people you really want to pull in, they might not have the same kind of idea. So you're basically putting a bias. So the best thing to do really is doing a random selection versus like saying, hey, for example, one thing you don't want to do for A/B testing, ideally, is you don't want to ask people to opt in. Essentially, because if you ask people to opt in, you're essentially getting people who, the people who opt in are going to be people who are different from the general population, right? They're going to be people who might have strong feelings in one way or the other. So really, ideally, what we want to do is like, okay, we're just going to randomly assign people, and those people are going to be part of our test, and that's going to be used to determine our hypothesis, or be used in our hypothesis test. Does that make sense to people? Okay. Any questions on kind of like how that random selection kind of works? Okay, so some quick things to note, which are commonly used. If you have some kind of ID, like let's say, for example, you use someone's like, let's say every user puts in their phone number and you put in something like, oh, if the first, I would say like the last digit of their phone number, if it's odd, you're in one group, if it's even, you're in another group. Would that be a good way to determine or a bad way to determine who's in your group?
Bad.
Bad? And can you tell me why? Or what might be why it might be bad?
You'd have to check to see if it's a true random sample of how many odd and even phone numbers you have in your data set.
Yeah, this can like give you some weird stuff. So like it might be random, but in reality, it's like you don't know if there's some relationship between the phone number and the person. And one like random example, let's just say this is true. I don't know if it is true, but let's just pretend this is true, that people who select their phone number, so maybe they have a business phone number, they always like to have the number end with 0 because for some reason, you know, business people or whatever like the number 0. You're going to have a selection bias in that sense where all the business people we put into one group or whatnot, or people who select numbers. So you always want to be careful of exactly how you're doing this. I've seen a lot of people like use like, for example, like try to use hashes and do like this random stuff, where in reality it's just like, oh, just do a random sample where you basically treat everyone equally. One thing to note though, is that sometimes random selection usually is not the best thing to do. Sometimes, I'm sorry, I don't know if I said that right, but random selection isn't always the best thing to do. So sometimes it makes sense to do a stratified selection, where a stratified selection basically says we break them into groups and you randomly select within those groups to make sure you have, what's it called, an equal number of people representative of the population. So for example, if there's just very few people who, I used a school scenario before with another cohort, is if you had a school of like, you know, like say first, second, third, fourth, fifth graders, right? But the second grade class is relatively small and you basically randomly sample, there's a chance that basically you won't have you'll skip over the second graders, and second graders won't be represented in your A/B test. So what you might do instead is like, okay, we're going to basically pick so many from first grade, so many from second grade, so many from third grade, so many from fourth grade, and randomly sample within those groups to make sure you have something that's representative of the actual sample. So sometimes it makes more sense to do stratified, though that can cause some extra little things to kind of consider. But for the most part, random selection usually is best for your A/B testing. Okay. Sound good? All right, awesome.